In our previous example, we calculated the probability of two events occurring at the same time. In particular, we imagined that we were a public health researcher and we wanted to know what's the probability of being economically poor and not having health insurance. We found that probability, that joint probability, is 0.09. But suppose you want to create a different measure of overall socioeconomic vulnerability. So you might say, well, okay, overall, the probability of having no health insurance and living in poverty, it's fairly low. I mean, from sort of a policy standpoint, it's probably too high. But we might say, okay, it's still 0.09. That's that joint probability. But we might say, well, what if we take a broader perspective about what it means to be vulnerable in a socioeconomic way for Americans? So we might say extreme vulnerability, so you're really in a bad situation if you have no health insurance and you're living in poverty. That's a really sort of worst case scenario. But you're still vulnerable in a socioeconomic way if you don't have health insurance, but you're not poor. Or we might say you're vulnerable if you are poor but have some kind of health insurance. So we might say, well, what's the sort of overall measure of socioeconomic vulnerability defined as somebody who has no health insurance, is living in poverty, or is living in poverty and doesn't have health insurance? To calculate this measure of overall vulnerability, we want to think about something called the addition rule. The addition rule, it's used when you have two events and you want to know the probability of at least one of those events occurring. So in our case, our two events are having no health insurance and living in poverty. And we want to know what's the probability of at least one of those events occurring. So let's think of these two events as A and B. The addition rule says the probability of A or B equals the probability of A plus the probability of B minus their joint probability. To put it another way, you subtract out the joint probability from the simple addition of the probability of A and the probability of B. Now there's an important caveat when we use the addition rule. When we talk about the probability of A or B, we have a very particular meaning. The probability of A or B, it's the probability that A occurs, that B occurs, or that both A and B occur. This is not the same meaning of or that people use in everyday language. In everyday language, you might say to a friend, are you going to the gym or are you going to the grocery store? Implicit in that is that you're doing one or the other. When we talk about or in the language of logic or probability, we're saying you can go to the gym, you can go to the grocery store, or you could do both. Now, people don't use or that way, but because probability is derived from logic, we use or based on the rules of logic. So when you hear or in the context of probabilities, it means A, B, or both. So when do we use the addition rule? When we have two events and we want to know the probability of at least one of those events occurring. So in this case, we want to know what's the probability of being poor, what's the probability of not having health insurance, or what's the probability of having no health insurance and being poor. So let's step back and just say something about notation. The probability of A or B, it's sometimes written using this notation from set theory. So you might see the probability of A or B as the probability of A, and then you see this sort of U, B. That just refers to the union of two sets. That's where the U comes from. It means the same thing as or. You might also see the probability of A and B is written as using this little horseshoe. That just refers to the intersection of two sets. The intersection, so if you have a Venn diagram, that intersection is just that overlap area. It just comes from the language of set theory. It means the same thing. So probability of A or B, same as the union of two sets. The probability of A and B, it's the same as the intersection of two sets. So let's look at this addition rule in terms of the Venn diagram. As I've mentioned earlier, joint probabilities expressed as a Venn diagram, they overlap. Okay, there's some sort of intersection, there's some overlap. For disjoint probabilities, the probability of A and B is 0. So there is no overlap. When we talk about the addition rule, The addition rule is that the probability of at least one of these events occurring, A or B, is expressed as the probability of A plus the probability of B minus the probability of A and B, minus that intersection. The reason we do that is we don't want to double count the intersection. If we add A and B and just say, well, that's the probability of A or B, we're actually counting that middle part twice, because the intersection is embedded in the probability of A, but it's also embedded in the probability of B. So you gotta subtract out that middle part. However, with disjoint probabilities, with disjoint events, the probability of A and B is 0. So the addition rule is actually a little bit simpler. The addition rule is simply the probability of A plus the probability of B, because the probability of A and B is 0. Let's break this down a little bit further, just to be perfectly clear what the addition rule is doing. One way to talk about the addition rule is that it's giving us the probability of at least one of these events occurring, and it's the overall probability of A, the overall probability of B, minus that intersection. And so you can see when we break down the Venn diagram, you can see that if we add A and B, and we don't subtract that intersection, that joint probability, we are in fact double counting that intersection. So here's an example of finding the probability of A or B. Suppose that the probability of A overall is 0.35, the probability of B overall is 0.7. If you add up those two probabilities, you're going to get a probability of A or B that's above 1. So you know that you're double counting that middle part. So you subtract out the probability of that intersection, which is 0.2, and then you obtain the probability of A or B as 0.85. Again, we use the addition rule because we don't want to double count that intersection. A different way of expressing the addition rule is in terms of only A and only B. So we might say the probability of A or B equals that joint probability of A and B plus the probability of only A and the probability of only B. To put it another way, the probability of A or B is the probability of A and B plus the probability of A and not B, and the probability of B and not A. When you break down this addition rule using these Venn diagrams, key point is you're just adding up these separate components to obtain the overall probability of A or B. So here's a similar example. Suppose the probability of A and B, that joint probability, is 0.2. The probability of only A, it's only the blue part without that intersection, is 0.15. And the probability of only B, that sort of yellow area ignoring the intersection, is 0.5. And so the overall probability of A or B is 0.85. Again, the addition rule is very useful for calculating the probability of at least one event occurring. So let's return to our health insurance example. Recall that earlier we found the joint probability of being poor and not having health insurance, but now we want to find this probability of being poor, having no health insurance, or having both conditions at the same time. And this is an idea that we're trying to calculate the probability of being overall, how vulnerable are Americans in a socioeconomic context. So the probability of being poor or having no health insurance is simply the overall probability of being poor, which is 0.38, the overall probability of having no health insurance, which is 0.12. But if we just add those two together, we're double counting that intersection, that probability of being poor not having health insurance. So we have to subtract out that joint probability of 0.09, and we get this overall probability of being socioeconomically vulnerable of 0.41. To put it another way, the probability of being poor or having no health insurance or having both poverty and no health insurance is 0.41. Just to kind of break this down, we can, this is equivalent to saying the probability of A or B is the probability of A plus the probability of B minus the intersection, the probability of A and B. So we have this measure of overall vulnerability. It's quite a bit higher than this measure of just this intersection, this extreme vulnerability. A different way of expressing this calculation is in terms of the alternative formulation of the addition rule. We can say the probability of being poor having no health insurance, it's that joint probability plus the probability of being non-poor and not having health insurance, and the probability of being poor and having health insurance. It's a slightly different calculation. To put it another way, we can view the overall measure of being socioeconomically vulnerable in terms of the probability of A and B, plus the probability of only A and the probability of only B. Again, it's a slightly different way of calculating this measure of overall vulnerability. So our conclusions, we say, well, it's actually quite probable that Americans are socioeconomically vulnerable based on this set of data. In fact, we can say that the probability of having some kind of vulnerability, defined in terms of having no health insurance or being economically poor, it's 0.41. So about 4 out of every 10 Americans are going to experience some kind of vulnerability. But that extreme vulnerability, the probability of being poor and having no health insurance, it's a lower probability. It's about 0.09. So we can see at this point, by treating a contingency table as a probability table, as a set of empirically derived probabilities, we're understanding, we're able to make conclusions about some important aspects of the world around us. The key idea is a contingency table. It can be converted to a probability table by simply creating a table of unconditional proportions. Each cell of this probability table gives us joint probabilities, the probabilities of A and B. And then the margins, they will give us the marginal or overall probabilities of A and B. So we might get the probability of A, the probability of B, but those joint probabilities are probability of A and B. And then we have this idea of the addition rule, and it can help us answer questions when we want to know what's the probability of at least one event occurring. To put it another way, what's the probability of A or B or both occurring? So with that, we've really begun our foray into the addition rule and working with probabilities.